following are Mrs. Mooney's notes for acceleration due to gravity. When an object is in free fall, that object is freely moving throughout the air. Nothing is pushing or pulling on that object except for gravity, which is the pull due to the Earth's mass. So the Earth is always pulling down on objects, and the resulting acceleration has a constant value of negative 9.81 meters per second squared. Negative because the acceleration always acts down. And the acceleration is always constant. Gravity never turns off. Objects that are freely moving through the air never have an acceleration of 0. It is always negative 9.81 meters per second squared. We symbolize the acceleration due to gravity as little g, more common than, sometimes you see it as a sub g, but more commonly little g. Little g has the value of negative 9.81 meters per second squared. Because we assume no air resistance in this class, the gravity acceleration due to gravity is always constant at negative 9.81 meters per second squared. The formulas used for free fall problems are the same as those used for accelerated motion. Those formulas we used in the last section. The only difference is that now we're moving in the vertical direction, not the horizontal. So replace your x's with y's. Also, you automatically know the acceleration. If an object is in free fall, you automatically know the acceleration. It's negative 9.81 meters per second squared. Also, some helpful hints in solving free fall problems. If the object is dropped, the initial velocity is 0, because the object is just held there at rest until it's released. Then gravity will begin to accelerate it downwards. If an object is thrown up, its velocity is 0 at the top of its path, because as soon as you throw an object up, its velocity immediately begins to slow. It'll slow, slow, slow until it comes to a brief stop at the top of its path before turning around and accelerating downward. Let's try a couple example problems. Suppose a gangster drops a spray can of paint from an overpass onto the highway below. If it takes 3.5 seconds for the can to hit the ground, A, how far did the can fall? And B, with what speed did the can strike the ground? In this problem, the spray can of paint was dropped, so the initial velocity is 0. We automatically know the acceleration, it's that due to gravity, and you were told that the can fell for a time of 3.5 seconds. So let's solve for how far the can fell in this 3.5 seconds time of fall. We'll start with the equation that we used in the last chapter to solve for displacement, delta x, equals the initial velocity times the time plus 1/2 the acceleration times the time squared. Replacing the symbols appropriate for free fall problems. So the change in vertical displacement will equal the initial velocity times the time plus 1/2 the acceleration due to gravity times the time squared. The initial velocity times the time is 0, because the initial velocity is 0. 0 times any amount of time is going to be 0. So this first quantity is 0. 1/2 the acceleration due to gravity, which is negative 9.81 meters per second squared, multiplied by the time squared. The seconds squared are going to cancel out. Multiplied to get a value of negative, because the can fell down, 60.1 meters. Now let's solve for final velocity, the velocity at which the can of paint strikes the ground. Now be careful, the final velocity is not 0. The can of paint, it hits the ground with some velocity and then comes to a stop due to the ground, but it does hit the ground with some final velocity. The initial velocity is still 0. The acceleration is due to gravity, negative 9.81 meters per second squared, and the time of fall is still 3.5 seconds. So we will go to the formulas that we used in the last section. The appropriate one is final velocity equals initial velocity plus acceleration times time, where the acceleration is due to gravity. The initial velocity is 0. Multiply the acceleration of gravity times the time. One of the seconds cancel out. Multiply, you get the value of negative 34.3 meters per second. Negative because the can fell down. The motion of an object thrown in the air is symmetrical. Initial and final velocities are equal in magnitude or size, but opposite in direction. For example, if I throw a baseball up with an initial speed of positive 2 meters per second, it will eventually slow to a brief stop at the top of its path and then return to a final velocity. By the time it comes back down to its point of release, the final velocity would be negative 2 meters per second. And time up equals time down. If it takes 3 seconds for an object to go up to the top of its path, it'll take 3 seconds to come back down. Let's try one more example problem. A ball is thrown straight up with a velocity of positive 15.5 meters per second, and is caught at the same position above the ground from which it was released. How high does the ball rise, and how long is the ball in the air? For this problem, we are given the initial velocity. I threw the ball up with an initial velocity of positive 15 meters per second. You automatically know the acceleration, that's due to gravity. And for this problem, I'm going to look at half the motion. I'm going to look at the portion of the motion from where the ball is first released to where it comes to a stop at its highest point, right before it turns around and begins to accelerate back down. And what we're looking for is the change in vertical displacement at its maximum height. The problem asked for how high the ball rose. Well, it reached its highest point, its maximum point, when it comes to that brief stop. So if I look at that half a motion, I'll be able to find its maximum height. And also, if I find the time it takes to go from the initial velocity of 15.5 meters per second to 0 at its highest point, if I find that time, that's the time up, then I can just double it, and that'll give me the total time in the air. So I'm going to go to the equation that is appropriate. Final velocity squared equals initial velocity squared plus 2 times the acceleration of gravity times the change in vertical displacement. Solving for the change in vertical displacement, which will give me the answer to the question that we're looking for, how high the ball rose. Well, the final velocity is 0. So plug in 0. 0 squared is just 0. Plug in the initial velocity, and then add 2 times the acceleration of gravity, and then we're going to solve for the change in vertical displacement, the max height. So doing the algebra, 15.5 squared plus 2 times 9.81, negative 9.81. Then subtract the 240.25 over to the left-hand side of the equation, and then you need to isolate your variable here, divide then the negative 19.62 into the 240.25. The second squares cancel out, one of the meters cancel out, so you're left with 12.2 meters, which meters is the appropriate unit for displacement. So the ball actually rose to a maximum height of 12.2 meters. Next, I want to find the total time the ball spent in the air. But remember, I'm only looking at half the path of motion from the time it left the hand at 15.5 meters per second until the time it reached the final velocity of 0 at its highest point. So I find the time it takes to go from the initial velocity to the final velocity, and that will give me the time up, and then I will double it to get the total time in the air. So the equation that we're going to use is final velocity equals initial velocity plus acceleration times time. Plugging in the variables that we know that the final velocity is 0, the initial velocity is 15.5 meters per second, plus the acceleration due to gravity times the time that I'm looking for. Then just do the algebra, solving for time, and that'll give me the time it takes to go up. 1.58 seconds. The total time in the air is time up plus time down. Remember, time up equals time down. So if it takes 1.58 seconds to go up, it's going to take another 1.58 seconds to go down. So 1.58 seconds times 2 gives me a total time in the air of 3.16 seconds. Do remember to keep track of signs. If an object is falling down or dropping, then the distance and the velocity are negative.